How are you guys today? Looks like some fun weather out there. So what questions do we have to start with?
Can we look at something from section 2.3? That's kind of what I was trying to figure out yesterday.
Sure. Okay, so draw a picture here. I've got this function 2x plus 7. The limit's 25 when I'm approaching 9. And we've got an epsilon value of 0.08. So that means that my tolerance for my output is 8/100. So from the output that I want to show that this limit approaches, which is 25, I want to go up 0.08 and I want to go down 0.08. Okay. So I go up to 25.08 and I go down to 24.92. And this is the epsilon band that I want to stay within. And to do that, this function, if I look down here, there's some delta band around the C value that I have to stay within so that my function stays within the horizontal band. Right? As long as I pick an X value in here, my function value is going to be in that horizontal band. If I pick a function value, an X value out here, that point on the function is outside this horizontal band. And so I don't want to pick these points. I want to pick the ones that are close to my input. So I have to figure out what delta, what's the maximum delta that lets me do this, because this wants the largest open interval, which does this. So I want to put 24.92 equals 2x plus 7, because that would give me the point where the graph of the function leaves this horizontal band to the left, right? That point is where the function and the bottom of the horizontal band meet, is going to be that point right there. And that's what you do to solve that. Y equals this equals that, which is y equals. So y equals, and you solve, you get x. The 17.92 over 2 equals x. So that's going to be 8.94, I think. No, sorry, 9.6, sorry, 8.96. Right. 8.96 equals X. And we do the same thing over on this side too. So this side was 8.96. This side, we're going to have 25.08 equals 2x plus 7. So that's going to be 18.08 equals 2x, or 9.04 equals x. So on this side, it's 9.04. But the delta that I get, it wants just the largest open interval for now. So we'll put in those two values. And so how far can you go left or right? You can go 0.04 from the middle. C was at 9, right? So if I go 0.04 left or 0.04 right, I get to those two values. And there's my delta. Does that make sense?
Yeah, it does. But why is the interval open and not closed?
Because you see this inequality right here with the epsilon is strictly less than epsilon.
Okay, yeah.
That means I can't include these points, right? So I want to actually be inside this horizontal strip, and the points aren't actually inside it, but it's where they start to become inside if you're within. Does that make sense?
Yeah, it does. I didn't see that sign.
Yep. So it's the strictly less than epsilon bit. Okay. Other questions? Yeah.
If it's not linear, like so one of the sides is bigger in that
Right.
first one, would you put like both of them to show them that first one, or would you take the less one?
So for the first one, it says the largest open interval. So you take the
like in the
entire thing.
In the in that like the open interval, do you take the less one inside there to both sides?
When you find your delta, you pick the smaller one. But when you find the largest open interval, you find both of them actually where they are.
Okay.
Does that make sense?
Yep. Yeah.
Okay. Other questions on this? Other things you want to talk about this morning?
Can we look at like the L'Hopital's rule?
Yeah. Okay, so on this one, I want a limit as x goes to infinity of this rational function, and the rational function goes to infinity on the top, and the rational function goes to infinity on the bottom of the fraction. Like the numerator, the limit of the numerator is infinity. The limit of the denominator is infinity. And so we get to use L'Hopital's rule because I have an indeterminate form there. of infinity divided by infinity. And so what you can do is you can take the limit of the derivatives. So we've got limit x to infinity, 5x cubed minus 6x, 7x cubed plus 7. So I've got infinity over infinity, so I get to use L'Hopital's rule. That's just going to take the derivative of the top part and the derivative of the bottom part individually. I don't use the quotient rule. And so the limit of the top is 15x squared minus 6. The limit of the bottom, sorry, the derivative of the top is 15x squared minus 6. The derivative of the bottom is 21x squared. And so I could take the limit of that, and that I can actually, well, let's keep using L'Hopital's rule because I can still go, this looks like infinity over infinity still. Take a derivative of the top again, I get 30x. Take the derivative of the bottom, I get 42x. Now I could just cancel the x's and I get 30 over 42 without any limit anymore because there's just a constant there. And I can divide by 6 on both of those, so 5 over 7. Okay, that was a straightforward one. Do we have questions on that one before I do something that's maybe a little trickier? If any of these look interesting to you, let me know. This one might be okay. Okay, so I want limit as x goes to 0, 9x squared over natural log of the secant of x. Is this in an indeterminate form? Well, let's see what the top does. 9x squared goes to 0 as x goes to 0. Natural log of the secant of x. These are just parentheses. The secant of x goes to 1 as x goes to 0, and the natural log of 1 is 0, so this also goes to 0. So this looks like 0 over 0. That says indeterminate. My screen's moving while I'm trying to write. Okay. So we can use L'Hopital's rule. Get this to 18x over the derivative of the natural log is 1 over the stuff inside times the derivative of the stuff inside which is secant x tangent x. The secants cancel. This simplifies to 18x over tangent x. X goes to 0, top still goes to 0, the bottom still goes to 0, still in an indeterminate form. L'Hopital's rule again. I'll get an 18 there. The derivative of the tangent is the secant squared. Okay, and as x goes to 0, the secant goes to 1, we said, so the secant squared goes to 1. This just goes to 18. Questions on that one? This one you have to manipulate a little bit to get into an indeterminate form of 0, 0. Because this right now looks like 0 times infinity. So to get it to be 0 over 0, I rewrite this as right. Cotangent is 1 over tangent, so I rewrite it as 1 over tangent, and then I have 0 over 0 now. And then we can do L'Hopital's rule from there. What do I do with this fraction?
Would you cross multiply?
Yeah, I would probably start with that. So we find a common denominator. And now as x goes to 6, the denominator goes to 0. The numerator goes to 0. So now I could use L'Hopital's rule now that I've got it into the 0 over 0 form. I was really hoping to see one where I had to take a log or use an exponential, but I'm not seeing any of those. Here we go. As x goes to 1, the base of the exponential goes to 1. The top of the exponential goes to infinity. So this looks like 1 to the infinity. This is an indeterminate form. And so what we do is we set L equals this limit. And then I take the natural log of both inside the limit and the L. Okay. Okay. And now I have a fraction, 4 natural log of x over 1 minus x. As x goes to 1, the natural log goes to 0, so that looks like 0 over 0 now. And then I can take L'Hopital's rule. Get 4 over x, because the derivative of the natural log is 1 over x. And then the derivative of the denominator there is a minus 1. Right. So that limit as x goes to 1 gives me just a negative 4. So the natural log of L equals negative 4, which tells me L equals e to the minus 4. So this is e to the minus 4. Okay, questions on that one? That was kind of the trickiest one we've seen so far. Okay. I just wanted to show you the technique where you use a continuous function on the limit, like exponential or natural log, and that was that one. Okay. Other topics you guys want to talk about?
Could you explain again how it differs if you're taking the limit from the left or the right? Like, how does it differ in your calculation?
Usually it doesn't so much unless the denominator is going to switch. Like, so the idea is, if I'm looking at this denominator of 1 minus x on the number line at 1, I've got 1 minus x here. It's going to be negative over here and positive over here, because I'm subtracting something smaller than 1 from x. The result's going to be positive. Here, the result's going to be negative. So if I wasn't looking at the natural log of x part, I was just looking at 4 over 1 minus x. Well, over here, I'm dividing by something really, really tiny but positive. 4 divided by something really, really tiny but positive would go to positive infinity. On this side, I'm dividing by something really, really, let's put the 4 in there. So this side's going to be negative, and so this side's going to be going towards negative infinity. Does that make any sense why it depends on which side of 1 you're at?
Yeah, it does.
Okay. And usually, yeah, it's just a sign thing. Or am I going to positive infinity or negative infinity? Sometimes you might have a step function or a piecewise function. And like, if I was coming in from this side, I'd be approaching whatever this y value is. But if I was coming in from this side, I'd be approaching whatever that y value is if you were doing it graphically. But algebraically, it's usually going to be, am I going to go to positive infinity or negative infinity? Other questions on that or otherwise?
Can we look at some trig inverse derivatives?
Mm-hmm. Try and find the derivative of the sine inverse. So this equation is the same statement as sine of y equals x, right? So I'm going to use implicit differentiation, and I'll get the derivative of the sines, the cosine. Then the chain rule says I have to multiply by y prime. And the derivative of x is just 1 if I'm taking everything with respect to x. So I get that y prime equals 1 over the cosine of y. And if I draw my triangle, x is equal to the sine. So my triangle is here, and this is y. The cosine of y would be this side. And this side is the square root of 1 minus x squared. So this is 1 over square root 1 minus x squared equals y prime. So my derivative is 1 over the square root of 1 minus x squared. So you do this with implicit differentiation. Does that ring bells?
Yeah.
Okay. Is there another one you want to look at, or was that good?
Not really. I mean, I was just trying to like just hit the topic, you know.
Oh, sure.
So
So yeah, this triangle picture is going to be kind of key to some of this stuff too. And that's a useful skill to have. I think we've done that a few times.
Can we quickly like just do a little overview of Newton's method?
Yeah. So the idea is you take x naught, and then you follow the tangent line back, and you get your next x. All right. So you're going to take f of x naught minus I want to go, how much is that? That's that divided by the slope. So xn plus 1 minus is equal to xn minus f of xn over f prime at xn. That's how that works. Because you want to take your original x, and you're going to move backwards or forwards depending on whichever the slope gives you. But you want to take away from your original x something that gets you closer to the root. And this is what you're going to take away to try and get you closer to the root. So let's try and approximate the square root of 2. So we want to solve this equals 0, which would give me a square root of 2. We're going to approximate it by starting with x naught equals 1. And then let's say x1 would then be 1 minus x squared minus 2 over 2x at x equals 1. So my first iteration gets me up to 1.5, which is a little too big. But x2, I'm going to take that 1.5, put it into the original function, And I'll get 1.5 minus 1.5 squared is 2 1/4. 2 1/4 minus 2 is 0.25. And this is going to be divided by 3. So that's going to be 1.5 minus 0.083333. Gets me to 1.416, which now is really getting pretty close to the square root of 2, because the square root of 2 is 1.414, right? So that's how we use Newton's method. Is that refresh
that's good.
memories?
Yep.
Okay. Let me just write down the iteration again. Xn plus 1. The next iteration of Newton's method takes the previous one and you take away the actual function that you're solving for the root at n, and then you're going to divide by the derivative at the previous iteration. Okay. Other questions?
Did you say for the test, you're going to maybe focus a little bit more on the harder sections and then like the limits on section 2 and stuff? Maybe not so many questions.
I guess I don't know what you mean by that.
Are you going to have just as many questions for like a section 2 as you will for section 5 and 6?
I mean, yeah, section 2 is part of 2, 3, and no, sorry. 2, 5, and 6 are together, right? Yeah, I'll try and do about 10 questions from 2 and about 10 questions from 5. I'll probably take questions from 6 instead of questions from 2, though. Probably. If that's...
Yep, that answered my question.
Okay.
Could we look at the mean value theorem a little bit too?
Yeah. So A and B, you get a continuous differentiable function. Point A, f of A, B, f of B. You get the secant line. The slope of the secant line is f of B minus f of A over B minus A. The mean value theorem says there exists C, backwards E, not a unique, I don't need an explanation, but backwards E, there exists C in the interval from A to B with f prime at C equal to this M, the secant line slope. You can kind of think of it as, well, to get from A to B, at some point in time, I have to be going the average rate of speed. If my rates of speed are continuously changing, I can't go always slower and ever get up there. If I'm always going slower, I'll never get there. If I'm always going too fast, I'll never get there. So at some point, I have to be going the perfect speed to get there with that average rate of speed. If everything's continuous. I mean, if I can jump around and stuff, then that's not necessarily true. But if it's continuous, then at some point I have to be going that average rate of speed. That's what the mean value theorem says. Let's maybe see if there's some questions we can answer with that. Okay, so it took 18 seconds for a thermometer to rise from -26 to 100 degrees Celsius after it was taken out of a freezer and put into boiling water. So that somewhere along the way, the mercury was rising at a rate of 7 degrees per second. So it moved 126 degrees in 18 seconds. And so if we take 126 by 18, you get 126 is 18 times 7. So 126 divided by 18 equals 7. That is equal to the slope of the tangent line, right? If my graph starts at -26 at 0, and 18 seconds later, I'm up here at 100. I don't know how this curved, but it went something like that. Somewhere in here, I'm going to have a slope of 7. Well, over here somewhere, because I want that to be the same slope as this. Does that make sense?
Yep.
So I don't know what it wants from me on this problem, but the closed interval for this application is 0 to 18. Because that's the time where it started changing and the time that we stopped changing. Is it continuous? Yes, because there's no jumps in temperature while the temperature is changing. Right. F prime, F represents the temperature, T represents the time, so it's the rate of change of temperature with respect to time. Is it differentiable? Yes, because the temperature changing doesn't just suddenly skip all over the place. Rates of change don't just go weird. So we have the mean value theorem satisfied for the conditions. We just said that that's 7, and that's degrees per second. And so the mean value theorem says there's at least one point C in the interval for which the rate of change is equal to 7. There's at least one point in C for which the derivative is 7, because we already calculated this. We knew that that was 7 for sure, but there's a place where we don't know what the derivative looks like, so it's A. There. And then we interpret that that means that there's at least one point in time between 0 and 18 seconds when the temperature is rising at 7 degrees per second, which is what they wanted us to prove. Questions on the thought process of using the mean value theorem there? Okay, other topics you guys want to talk about?
Can we look at some related rates? I think it's section like 310.
Yeah. So let's try and draw a picture. So I got this particle, it's moving in space with dx equal to -3 meters per second and dy equal to -2 meters per second. We're going to pass through this point at 15.8. X is changing this way at 3 meters per second. Y is changing this way at 2 meters per second. And we want to know how much is d changing in as a rate of speed. So d squared is equal to x squared plus y squared. Distance to the origin, right? Are we good with that?
Yeah.
Okay. If I want to find d dt, that's going to be 2 times d times, sorry. We're asked to find this. So I'm going to take the derivative of this. I'm going to take the implicit differentiation of the equation that I have. It's going to give me 2d dt equals 2x dx dt plus 2y dy dt. Are we okay with that?
Yeah.
Differentiated everything with respect to t. So I'm going to cancel all the 2's. I still want to find d dt. So that's going to be x times dx dt plus y times dy dt divided by d. Okay. And our situation, I've got dx dt is -3, y dt is -2. And the original distance there is the square root of 15 squared plus 8 squared, which I think is 13. No, sorry, 17. Pretty sure, let's see, 225 plus 64 is 289. 289 is 17 times 17, I think. Yeah. So our original distance is 17. X was 15. and dx dt was -3. Y was 8. dy dt is -2. And d is 17. So I'm going to have -45 minus 16 over 17 is -61 over 17. Okay, questions about that one? So what did we do? We found an algebraic relationship that I could differentiate, that could compare or relate the rates that I have with the rate that I want. I want to know what the distance is doing as a rate of change, and the rate that I'm looking for is distance divided by time, right? That's the speed. So I need an expression with distance in it that I can differentiate with respect to time to get the rate of change of distance with respect to time for speed. So I come up with the equation for the distance, and then when I differentiate it, I realize that I need to know, okay, what's the change in the x, what's the change in the y, which were given to me, so that's good. And so I just work forward from there, plugging in the numbers that I have, and that gives me my rate of change. Because I have the dx dt and the dy dt, I know that I should probably be comparing x and y to the distance, and that's kind of why I do it with the x's and the y's. Does that all kind of make sense with that little bit of reflection there?
Yeah.
Okay. Might have time for one more. Thoughts on what it should be?
Can we do a ladder one, like the falling ladder?
Sure.
Related rates.
Let's use those same numbers. So I got a 17-foot ladder. It's 8 feet here and 15 feet here. And let's say I want to know it's sliding this way at a rate of 1 foot per second or something. When it gets to 15, this will be at 8, right? I want to know how fast this end of the ladder is changing when it gets to 8 feet off the wall. Does that make sense?
Yeah.
Okay, so how do I want to set this up? Let's call this Y, let's call this X. I know that X squared plus Y squared equals 17 squared. And I just want to compare dx dt with dy dt. So I'm going to take everything here with respect to t. So 2x dx dt, 2y dy dt equals 0. So I get that x dt equals minus y dy dt. So if this is equal to, would we say 1? And x will be 15 at that point. So 15 times 1 equals minus. Y will be 8 at that point times dy dt. So dy dt will equal minus 8 over 15. So a little less, or a little bit more than half a foot per second is what that will be when we're out here.
Why is it minus 8 over 15, not minus 15 over 8?
You're right. Because I'm going to divide by 8, not by 15. Okay. A little less than 2 feet per second. That makes a lot more sense because it should be falling faster. Okay. Other questions on that one? Okay. If you have other questions, let me know over email or something. And I am feeling pretty good this morning, so I should be able to get the spreadsheet up and posted for you, some grades. Stay warm today. Good luck. It's been a good semester. If you haven't filled out evaluations and you still can, go for it. Otherwise, I think it's been a tough, but I think it's been a good semester. Good luck.